I'd like to talk about finding the inverse of a matrix. Before we do that though, let me remind you why we'd want to find the inverse of a matrix. Suppose we were solving this system, 3x plus 14y equals 11 and 2x plus 9y equals negative 4. We saw in a previous video that you could rewrite that linear system as a matrix equation where it looks like this: 3, 14, 2, 9 multiplied by the column matrix, that is x over x and y, equals 11, negative 4. Now if we write these matrices as A for this matrix that is the coefficients of our variables, and capital X, which represents the matrix that contains our variables, and that equals B, those are our constants, we have an equation to solve that we would like to solve for X. So if we multiply the equation by A inverse of X, A inverse, on the left side of each of the expressions, then we'll have A inverse times A, which we know is the identity matrix, multiplied by X, equals A inverse times B. The identity matrix multiplied by X is just X, and we have A inverse times B. So we would have an equation that allows us to very simply find the solution to the system if the inverse of A were known. So what we're going to do now is find the inverse of 3, 14, 2, 9. So let's start that on another piece of paper. Here it is. A equals 3, 14, 2, 9. And we're going to find A inverse. Now here's the process that we use. We set up a matrix that has A on the left, so 3, 14, 2, 9, and it has the identity matrix on the right, so 1, 0, 0, 1. And our job is to use the elementary row operations so that we end with the identity matrix on the left, and on the right hand side we'll have the inverse. So here's what I just said. We're going to start with this matrix, that's what we have. We're going to use our elementary row operations until we have the identity matrix on the left and our inverse will be on the right. So let's do it. So remember, our elementary row operations that we can use are allowing us to interchange any two rows. And we only have two rows, so we can interchange them if we'd like. We can multiply a row by a non-zero constant, or we can add a multiple of one row to another. Those are the three things that we can do. We're going to put a 1 here first and a 0 beneath, much like we did when we were solving systems using Gaussian elimination. So let's start. We can put a 1 here first. We have a couple of ways to do it. One, we could divide by 3. I'm gonna choose not to do that because I see another option. But if I didn't see anything else that seemed reasonable, I could just divide by 3. But I notice row 1 minus row 2 would give us a 1 in the upper left right here. So let's do that. We're going to have row 1 minus row 2, and we're going to put the result in row 1. So let's do that. So we have 3 minus 2, that's 1, and that was the goal. 14 minus 9 is 5. 1 minus 0 is 1. 0 minus 1 is negative 1. And row 2 is unchanged. Don't lose sight of what we're shooting for. We want the identity matrix over here. That means 1 along the main diagonal and 0s everywhere else. So for this 2 by 2 matrix, it's a 1 here and here and a 0 here and here. So after I have a 1 here, I'm going to get a 0 beneath. So I'm going to multiply row 1 by negative 2 and add. So negative 2 times row 1, we're going to add that to row 2, and we're going to put the result in row 2. So let's do that. So we have negative 2 times 1. Let me write row 1 first. Now here we go. We're multiplying by negative 2 and add. And remember, as I've mentioned in previous videos, if you need a piece of scratch paper to do the arithmetic, go ahead. Here we go. Negative 2 times 1 plus 2 is 0. Negative 2 times 5 is negative 10. Plus 9 is negative 1. Negative 2 times 1 is negative 2. Plus 0 is negative 2. Negative 2 times negative 1 is 2. Plus 1 is 3. And our matrix looks like this. Our next place to go is right here. We need this to be a 1. And notice we can easily get that if we just multiply row 2 by negative 1. So let's do that. So I'm going to move up here. Let me show we're coming up here. And we're going to multiply row 2 by negative 1. And we're just going to replace row 2 with the opposite of row 2. So here we go. Row 1 is unchanged. And row 2, we take the opposite of each entry. So we have 0, 1, positive 2, and negative 3. And now we only have one more entry to take care of to make this be the identity matrix on the left. We need a 0 right here. So we're going to multiply the second row by negative 5 and add it to the first row and put it in the first row. So we'll have negative 5 times row 2. We'll add that to row 1 and put the result in row 1. Remember, when you're using a combination of row 1 and row 2, you can put the result in either row 1 or row 2 mathematically. Either is fine. So here we go. Row 2 is unchanged, so let's just put in our 0, 1, 2, negative 3. So we're multiplying by negative 5 and adding, and notice because we have a 0 here, we don't lose our 1. So negative 5 times 0 is 0, plus 1 is still 1. Negative 5 times 1 is negative 5, plus 5 is 0. Negative 5 times 2 is negative 10, plus 1 is negative 9. Negative 5 times negative 3 is 15, plus negative 1 is 14. So we now know we have the inverse of A. So A inverse is equal to negative 9, 14, 2, negative 3. Now let's head back to our system right here. Remember, we were trying to find the inverse of A, so we could find the solution to this system. And now we know the inverse of A. So for this particular solution, here was the matrix that was A. We have just found the inverse of that matrix right here. So X, or XY, equals A inverse. Let's just copy that down. Let me move this up so we can see both at the same time. Maybe we can see both at the same time. So A inverse is -9, 14 to -3. We're going to multiply that by 11, -4. So we have X, Y equals, and now we're going to do the arithmetic when we multiply these matrices together. 9 times 11 plus 14 times -4. So we have -99 plus -56, which is -155. Now we have the second row in this column, +22 and a +12 is +34. So we now know the solution to this system is the ordered pair, -155, 34. But notice after we found the inverse of the matrix, the process of solving this system was very short. Most of the work ended up being in the process of finding the inverse. So one benefit of this particular strategy is if you had a number of systems to solve that had the same coefficients for X and Y. For example, I just listed a few. This is the system that we just solved, and we saw that -155, 34 was a solution. But what if you wanted to just tweak the system a little bit and you had different constants? We could still use the same inverse, find the solution very quickly. Here's another system, same coefficients for X and Y, just different constants. We still have A inverse as -9, 14 to -3, multiply by the constants, and you can very quickly solve multiple systems if each of the systems have the same coefficients for X and Y. So that's one benefit of this particular strategy. Let me mention one more thing about finding the inverse of a matrix. Suppose we have a 2x2 system. There is actually a formula for finding the inverse of a 2x2 matrix. I said system, I meant a matrix. Suppose you have the matrix was A, B, C, D. I'm not going to prove it, but I will just tell you that A inverse, if this is A, then A inverse can be found by multiplying 1 over AD minus BC by the matrix D opposite of B, opposite of C, A. So for a 2x2 matrix, there does exist this formula. So if you wanted to use this formula and you had it memorized, and you had A equals 5, 2, -4, 11, and you were going to find A inverse would equal 1 over, now the product of AD minus BC, that is 5 times 11 minus -4 times 2. 5 times 11 minus -4 times 2. So we'll have a scalar. Remember, a scalar is just a real number there. and we'll multiply that by this matrix. Notice on the main diagonal, that's from upper left to lower right, we switch those entries. A and D get switched and become D and A. So 5 and 11 switch, and we have 11 and 5. And in the other diagonal, we just change the signs. So -4 and 2 will become 4 and -2. And let's do the arithmetic. We have 55 plus 8, that's 63. So it's 1 over 63 times this matrix, 11, -2, 4, 5. So the inverse of A is equal to 11 over 63, -2 over 63, 4 over 63, 5 over 63. And we have the matrix, or the inverse of the matrix. Now let me just mention, here was the formula we used, and here was our result. And that's a very nice formula if you have a 2x2 system, but we don't have this nice formula for a 3x3 system. So we're going to do one more problem, and we're going to find the inverse of a 3x3 matrix. So here we go. I'm going to move the camera up a little bit so we have a little more space here. And we're going to let A equal, let me make sure I'm in the region that we can see. We're going to let A equal this matrix. It's going to be 4, 2, 3, 3, 3, 2, 1, 0, 1. And our goal is still to find A inverse. And here we go. Our task is just as it was on our previous one where we didn't have the formula, where we were using the elementary row operations. So let's jump in. We will have 4, 2, 3, 3, 3, 2, 1, 0, 1. And on the right-hand side, we have the identity matrix. Our task, remember, is to use our elementary row operations so that we end with the identity matrix on the left, and on the right-hand side, we'll have A inverse. So let's get started. On this particular problem, there are a few ways that we could get a 1 on the upper left, because remember, that's where we start. You could just divide by 4. That's not my preference. I could subtract row 1 minus row 2. That would be pretty nice. But even more straightforward, when I see a 1 here, I think of switching or interchanging the two rows. And to me, that's the simplest. So that's what I'm going to do. Row 1 and row 3 will be swapped or switched. So my new matrix is 1, 0, 1, and make sure these come along with it. 0, 0, 1, 3, 3, 2, 0, 1, 0, and 4, 2, 3, 1, 0, 0. Okay, so we have our 1 here. Now we need zeros beneath. So I'm going to multiply row 1 by -3 and add it to row 2. Remember, I'm getting a 0 here. That's my goal. So -3 times row 1 plus row 2, and we're going to put the result in row 2. Let's do that. Row 1 is unchanged. So we have 1, 0, 1, 0, 0, 1. And here we go. -3 times row 1 added to row 2. -3 times 1 is -3, plus 3 is 0. -3 times 0 is 0, plus 3 is 3. -3 times 1 is -3, plus 2 is -1. And again, go to scratch paper to do the arithmetic if you need to. -3 times 0 plus 0 equals 0. And I will tell you, as you practice this, you get more efficient at doing the arithmetic. -3 times 0 plus 1 is 1. -3 times 1 is -3, plus 0 is -3. And at the same time, as I get this 0 here, I can get a 0 here. We can do that in the same step. So let's multiply row 1 by -4 and add it to row 3. So -4 times row 1 plus row 3, and we'll write that result in row 3. We can take care of those at the same time. So here we go. We're multiplying by -4 and adding. So -4 times 1 plus 4 is 0. -4 times 0 is 0, plus 2 is 2. -4 times 1 is -4, plus 3 is -1. -4 times 0 plus 1. -4 times 0 plus 0. -4 times 1 plus 0. And we're here. So we have our 1 and 0s beneath. Remember, next we move to put a 1 right here. I could certainly divide by 3. I'm going to choose not to because I see another option, and that is taking row 2 minus row 3 and write the result in row 2. So let's do that. So let's come up here. Coming up here, and we'll have row 2 minus row 3, and we're going to put the result in row 2. So row 1 is unchanged, 1, 0, 1, with our 0, 0, 1. And now we're going to do the subtraction. Here we go. 0 minus 0 is 0. 3 minus 2 is 1, and that was our goal. -1 minus -1 is 0. 0 minus 1 is -1. 1 minus 0 is 1. -3 minus -4 is 1. And let me write in row 3. And here we are. Now we need a 0 here. We've taken care of the 1, 0's beneath. We have the 1, 0's beneath, or in this case, just this spot. We need a 0 right here. I'm going to multiply row 2 by -2 and add. So -2 times row 2. We're going to add it to row 3, and we're going to put the result in row 3. Here we go. First row is unchanged. As is the second row. And now here we go. -2 times 0 plus 0. -2 times 1 plus 2. -2 times 0 plus -1. -2 times -1 plus 1. -2 times 1 plus 0. Negative 2 times 1 plus negative 4. We're getting closer. Let's see. I know I could add these 2 rows to get a 0 here, but I'm going to be systematic the way I always do. I always focus on getting 1 on the main diagonal and 0s beneath here before I worry about any of the entries up here. So that's what I'm going to do. Notice we can get a 1 here very easily just by multiplying row 3 by negative 1. So let's do that. Negative 1 times row 3. And we're going to put the result in row 3. So we have 1, 0, 1, 0, 0, 1. Let's see, row 2 is also unchanged. And row 3, we're multiplying by negative 1. So it's now 0, 0, 1, negative 3, 2, 6. And now I only have 1 more entry that I need to take care of to have the identity on the left, and that is I need to get 0 here. And if I multiply row 3 by negative 1 and add it to row 1, I will get the 0 here. Another way of saying that is taking row 1 minus row 3. So let's do that. Row 1 minus row 3, and we're going to put the result. Remember, if you use row 1 and row 3, mathematically you can put the result in either of those rows. I'm going to put the result in row 1. So here we go. Let me make sure you'll be able to see it. I think we can squeeze this in. So rows 2 and 3 are unchanged. And here we go. It is row 1 minus row 3. Put the result in row 1. So 1 minus 0. 0 minus 0. 1 minus 1. And now notice we have the identity matrix on the left. That's what we needed. 0 minus negative 3. 0 minus 2. 1 minus 6. And we now have A inverse. A inverse is looking at us right here. So A inverse is this matrix. 3, negative 2, negative 5, negative 1, 1, 1, negative 3, 2, 6. So if we were to multiply these 2 matrices together, remember what this means. If they're inverses, if we were to multiply these 2 matrices together, we would get the identity matrix. Now let's use this information just to solve a system. I'll feel better if we've used it for something. So here's our system that we'll solve. It is 4x plus 2y plus 3z equals 6. 3x plus 3y plus 2z equals 1. X plus z equals 8. Now notice I let A equal the matrix that comes from the coefficients of our variables. So our solution to this system can be found by multiplying A inverse times B. So that means X, Y, and Z would equal the product of A inverse. Remember, here's our A inverse over here. Let's write it down. 3, negative 2, negative 5, negative 1, 1, 1, negative 3, 2, 6, times the matrix that is 6, 1, 8. So here is our system where we have found the inverse of the matrix A, and let's just multiply these together and see what we get. So remember, we multiply, 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 and then we add those together. So we have 18 plus negative 2 plus negative 40. Let me write that down. 18 plus negative 2 plus negative 40. And we'll do the arithmetic in just a moment. Negative 6, I'm using row 2 and this column. So negative 6 plus 1 plus 8. Negative 6 plus 1 plus 8. Then we have negative 18 plus 2 plus 48. So negative 18 plus 2 plus 48. So we have X, Y, and Z, and it will equal 18 minus 2 minus 40 is negative 24. Negative 6 plus 1 plus 8 is 3. Negative 18 plus 2 plus 48. Let's see, we have 30 when we add those. Plus 2 is 32. So the solution to this system is the ordered triple, negative 24, 3, 32. And I hope you will practice finding the inverse of some matrices so that you can solve some systems.